In today's lesson, we're going to talk about relations and functions. So we're going to go through relations first. A relation is essentially just a way to relate one numerical value to another numerical value. So an example of this would be like if you're at the grocery store and you could describe the relationship between how many apples you have and the costs of the apples you have. So in this case, we're relating the how many apples you have to the cost. Yep. And another example of this could be like the temperature of the day, temperature at the time of the day. So in this case, we're relating the outside temperature and what time of the day it currently is. So there are several ways to basically describe or represent relations. So one of the common ways you'll see it is in a table of values. So you might have seen this in junior high and probably elementary as well. So for example, we have a table of values which relate the number of apples. Yep, table of values. So we could have one column where it's essentially the number of apples we have, and another column where we have the total cost.
So number of apples?
Yes. Then we have total cost. And in this table, we can have things like if there's 0 apples, there's obviously 0 cost, unless you're at Costco, which you have the membership thing.
All right.
Yeah. And then if you have 1 apple, it could be like the total cost is $2. And then 2 is 4. And then 3 is 6. And so on. There's like a pattern where we add 2 every time. Basically, the cost of the apple is 2. So this is one way we can express a relation. So in some cases, with relations, especially with table values, you might get questions where it's like fill in the blank. So for the example above, maybe instead of putting all the numbers there, we could be like, oh, we don't know how many apples are for the value $4. And you have to fill that in. It's essentially just pattern matching. So if you can find the pattern in the table, you can pretty easily solve that question.
Yeah, we should do an example. So for this case, the stable values, we could have a question that asks how many apples would cost $12 and how much money would 7 apples cost you? And in this case, we can see that the pattern is simply multiplying the number of apples by 2. So total cost is equal to 2 times the number of apples. So if we have $12, then we have 6 apples, and we have 7 apples, then we have to spend $14. Hopefully that makes a little bit sense.
Okay, so next up, we're going to talk about independent and dependent variables. So for the example above in the table of values, there's going to be a value which is independent, or in a science class, you might have called it manipulative. So yeah, that might be the science class term. And then you also have the dependent variable, which is kind of like the responding variable. Yeah, so the names of these variables kind of suggest what they do. So for the independent, it doesn't have to rely on anything. You could change its value and nothing much is going to happen. But the dependent variable relies on the independent variable. So if you change the independent variable, the dependent variable has to change. Or it doesn't, but it just has to be somehow related to the independent variable. So for the example above, where we have the apples and costs, we can kind of identify the independent variable, which is the number of apples we have, because we can just pick up more apples or put down more apples. And then the dependent variable will be the cost. So we calculate the cost based on how many apples we have. We can't have the cost as an independent variable because it's not that we're paying $12 and in our cart we somehow have 6 apples. It's more of like we have 6 apples in our cart and we have to pay $12.
Yeah, like another example of this would be like the weather of today, right? So for example, if today the temperature was around 27 degrees Celsius, 27 degrees Celsius, you would say that 27 Celsius relies on what day it is today. So yesterday, it probably would not have been 27 degrees. So in that case, today, or I guess the day would be the independent variable because it changes, and the temperature would be the depending variable or dependent variable because it relies on what day it is today. Usually, it doesn't go the other way around because we don't usually say it's 27 degrees, so it must be August 5th, if that makes sense.
Yes. And the next method we're going to talk about to expressing a relation is graphing. So you might have already known this. We kind of draw a graph and it's just ordered pairs. So we put the points on the graph. And here we can kind of link it with independent and dependent variables. So in graphing, usually, well, most likely, unless your teacher does something weird, but the x-axis will be the independent variable. So it's the one that changes. And the dependent variable will be the y-axis. So it's a result. So with the example above with the apples again, here the x-axis will be the number of apples we have. Get 4 apples. And then the y-axis will be the total cost. And here we could express the relation by drawing points on there. So 1, 2, 2, 4. I don't know if that line works.
Okay, it's a bit off, but my scale is a bit off. It's fine. Like that.
Yeah, I think that works. But like,
Yeah.
here, actually, we'll talk about this a little later.
Yeah.
Okay.
I mean, for like usually you want to have even spacings. So in this case, I didn't have even spacings because I tried to save space. I didn't want to go out of boundaries, but usually you should have even spacings. What do I mean by that? Uh, if okay, so you see how on the x-axis I labeled each unit as this distance, but on the y-axis I labeled each unit as like half of this. Usually they should be the same, but because my y-axis requires a lot more numbers, I just condensed it. But usually you shouldn't be doing this.
Yep. Okay, so the last method of expressing relations that we're going to talk about is called mapping. You're probably not going to encounter this method a lot in high school, but it's just something we have here. So you might as well just know it just in case your teacher has it. Okay, so the way that we perform mapping is that we kind of separate the independent and dependent variable into 2 groups. So we kind of draw a circle like a set, and then we put all the independent variables in one, preferably on the left side, and the dependent variables on the right side. So here we can have independent, it's like 0, 1, 2, 3, 4, again with the apples example. And then on the right side, we have the dependent. So it's like $2, $0, $2, $4, $6. Yeah, it doesn't have to be in order. And then what we do now with mapping is that we kind of draw an arrow or line between the independent variables and the dependent variable that it matches. So when we have 1 apple, we have $2, so we draw it to 2. When we have 2 apples, it's $4, so we draw it to 4. And yep, $4, 4 apples to $8. So this will be mapping. And in some cases, you would also encounter where 2 different independent variables match up to the same dependent variables. So you don't have to basically write a separate number for that. So for example, maybe not the apples example anymore, but maybe we have somehow like a number 17 and it can match up to like, yeah, we could just write some random numbers in there.
Let's do like the temperature of a day.
Oh yeah, that works. Yeah, so we can be like, we could put like, yeah, August.
When?
Yeah. And then we have like, yeah, 26 degrees, 28, some pretty good numbers. So maybe on August 1st, it was like 28 degrees. So you draw a line, and then August 2nd, it was like 26 degrees. And then maybe for August 3rd, it was also 28 degrees. So we just draw another arrow to the same value. And then August 4th, we have 27 degrees. Yeah, so it kind of gets complicated when you have a lot of values because you have a lot of lines overlapping. So this is why high school teachers don't really prefer this method.
Yeah, like it's never gonna be on tests. Well, not for my class. It wasn't
Yeah.
on test. Usually just remember the relation table values and the graphing method. Mapping, you don't have to worry about it so much.
Yeah. Just know it's a possibility, but you don't have to like study it in detail.
Yeah, exactly.
So should we do an example for them to do?
Yeah, sure.
Okay, so we can do like a fill in the table. So we could have something like the column X and Y. Oh, wait, that's a pretty nice way to draw a table.
Yeah. I don't know why, but drawing on an iPad makes everything so like slanted.
Now we can have X, Y, and for the X, we can have 1, 3, and then a blank, and then 7, 9, and then another blank. And then for the Y, we have 6, blank, 4, 3, 2, and 1. So you guys can fill in the values in the tables. Not sure how you're gonna really type this in chat, but try your best.
Just top to bottom. And also
Yeah.
you have to clarify that this is a linear relationship.
Oh yeah, that's very true. Wow, I wonder what this could possibly be. Yeah, I wonder too.
Yeah. Okay.
Yes, Edward, you got it right.
Wow, good job. Wait,
Yes,
5, 11, 5? Yeah.
511 Y5. Okay, yeah. Okay. The follow-up for this is to do it in mapping, but I don't think you guys can do that in the chat. So should we just do this together or do we want to just skip it?
We could just skip it.
Okay.
Upload file. I don't think that's gonna be very time efficient, but
Yeah. I
I
think
mean,
that was,
we can do a quick one, I guess.
yeah. Let's just do a mapping one for the example above.
Okay. So
I mean, we could also like have you guys screen share a whiteboard and then you guys do it, but I think that's just gonna be a mess.
yeah, that's just gonna be a mess. No point. 1, 3. Is this a question or do we just like draw out the?
We just map it. Just draw it in the mapping format.
Oh, okay.
This is not really complicated, is it?
Yeah. I mean, only uses for like small number of values, but if you have a large number of values, it's gonna take you a long time,
Yes.
like
Yeah.
what David said.
I think that was all about ways of expressing relations. Okay, so we're gonna move on to discrete and continuous lines. So wait, Kevin, can we scroll all the way back up to your graph?
Oh yeah. Oh, graph. Like,
Okay. So in this case, a discrete and continuous lines, basically just a discrete line. Well, a discrete line is not really a line, but a discrete line is just where you have the values by itself. So you have points on a graph, and there is no line going through them. And then continuous lines is kind of what Kevin has here on the graph. It's where a line goes through all the possible points. And the definition for a continuous line is where you can like put down your pencil and then draw a line through all the points without lifting your pencil. But that's not really a good definition because you kind of do that with every possible graph.
I think words are not the best ways to describe like discrete and continuous lines.
Yeah.
I think we should just like draw it out.
Yeah, let's draw a discrete graph and a continuous graph.
Yeah. So in a discrete graph, you see that each x value are going to be by themselves and they're not connected to other x values. So for example, we could have something like this. In this case, the x values do not form a line because they're all on their own. And what this really means is that x cannot be any values in between these values. So for example, if we 2, 3, 4. So for example, if we buy one apple, this would cost us $2. If we buy two apples, it would cost $4, and so on. What this graph really tells us is that we cannot buy any non-integral values. So we cannot buy 1.5 number of apples. We cannot buy 1.7 number of apples. We cannot buy 2.5 apples. So only use discrete graphs when x cannot take on certain values.
Yes. And a continuous line, a continuous graph is kind of like the opposite of this, where we can draw a line through all the points. And it means that any value between the points is also a valid value. So an example of this would be like the temperatures. You're not going to have all of a sudden the temperature go up by 10 degrees in like the next instant. What's going to happen is that the temperature is going to go up slowly and go through all the possible values before reaching the next point. Oh, good to point out that it's in Celsius.
Yes. Oops.
Oh,
I should draw. Okay, so when you see the scribble line, that means we're condensing a part of the axis. So like we can start at 26, 27, 28, 29, 30. So what this scribbly line mean is that we just ignore everything from 25 to 0. Okay. So in the temperature case, we might have something like this. Because the temperature is not gonna instantly like transfer from 27 degrees to 28 seconds in an instant, right? It's not gonna be like 28 degrees right now. In the next second, it'll be 27 degrees. No, that's not what happens. It goes continuously. So for the temperature case, we have a continuous graph, while for the number of apples, we have a discrete graph. So does that kind of like make sense? And we could always do more examples if something is confusing. Okay, so for a discrete graph, the x values can only be certain numbers, right? It could only be some specified numbers. However, on continuous graph, the x value can be any number, anything, right? So yeah, let me just explain again. For the number of apples you can buy, it's not like you can go to the supermarket and buy 1.5 apples. You can only buy full number integer number of apples. But for the temperature, it's you can take on any values between like any values between two temperatures. There's specifications for x and for continue. Yeah, exactly. But I mean, there's still some restrictions, but like the graph is continuous. So in this case, like x cannot be negative, but when x is positive, it can be any number. David, do you have anything to add or?
no, not really. I think you explained it pretty well. But yeah, it's just like it kind of tells if you if you can pick between a discrete and continuous graph for an answer, it kind of helps tell the marker that you understand that what the question is talking about. So kind of like when you have a question that involves a number of people in a classroom, you're never going to use a continuous graph, because what that's telling other people is that you're thinking there can be half of a student, right? Yeah.
Yeah, that's a good example.
Yeah, so you kind of need some background context for the question and some background knowledge to like answer these questions pretty well. So you kind of gotta like pick up skills to like learn what time to pick between a discrete and a continuous graph.
Yeah, yeah, David, you explained it really well. Uh, they're not always positive. I'm just saying, like, even for a continuous graph, you can't take on every single value on the number line. In the values that it could take, though, it's continuous. So maybe we should just do a couple more examples.
Yeah, we can do like distance over time.
Yeah, okay. So distance over time would be a continuous graph. Do you want to explain like why?
Okay, so should we draw the graph first? Yeah.
Yeah, that's a good
Okay.
idea.
So the reason why it's a continuous graph is that if you're traveling in a car, your car is not really teleporting along the way. So you're not going to go from at 1 second, you're at zero distance, to you're at 2 seconds, you're at like 10 meters away now with like no travel time in between. What's going to happen while you're traveling is that in between the 1 second and the 2 seconds, you're actually traveling from like, for example, okay, if we look at the graph, right? So if we label like 0 seconds, 1 second, 2 second, oh,
I was just typing his question.
oh yeah, discrete. Okay. Yeah. So your car, so between 1 second and 2 seconds, your car is not teleporting from one distance to the other distance. What's happening is that you're actually traveling that distance. For example, maybe at 1.5 seconds, we traveled at 7 meters. And at 2 seconds, we traveled like 10 meters. And at like 2.5 seconds, we traveled at like 13 meters.
Yeah. So I mean, if you think about it, like, this is a car that doesn't look like a car, but you get the
UFO.
across. Like, when the car is moving, it's gonna move very slowly, right? It's gonna like not be teleporting, but instead it's gonna move very slowly forward at a time. So this is why we use a continuous graph instead, to show that the car is moving. The car can be like the car is moving every single instant. If we were to use a discrete graph for the movement of a car, then that would be like saying at time 0, the car is here. Then at time, I mean, like 1 second later, the car instantly teleports from one location to another. Another example for a discrete graph would be like, David, what is a good discrete graph?
Oh, that's a really good question. What about like students in the classroom for time of day?
Oh yeah, yeah.
Yeah, so for example, like I don't know, 9 a.m. there's gonna be 0 students. At like 12 p.m. Wait, not 12 p.m. Okay, 11 a.m. there's gonna be like 36 students.
Well, but in that case, like the hour is the independent variable, so like couldn't wouldn't it be like a step graph?
That's true. Okay, wait.
Because we can only have
Huh.
discrete variables on the independent axis.
Yeah, what is a good example?
Uh,
Here, guys, if you have an example, post it in chat.
yes, discrete graph. Okay, we can do test questions answered correctly.
Okay, that's pretty good.
Yeah. So like the number of people who answered a question right, and the question number, I guess.
Yes, number of keys on a keyboard is a discrete value, but we're not sure how to relate that with another variable.
Yeah. But if you can relate it to something, that would definitely work.
Yes.
So maybe it looks something like this.
Dollars per key. Yeah, that's pretty good.
Oh yeah, dollars per key. Yeah, that's a brilliant example. But anyways, for the question number, like David, do you want to explain it or should I?
You want to? I
Sure.
can do it. Okay.
So on a test, each question is labeled number 1, number 2, number 3, number 4, and so on, right? So when we say how many people answer the question, right? We usually do a discrete graph because questions can only take on integral numbers. I mean, I think that's pretty confusing, but like you can't have question number 4.5, right? It's either question 4, question 5, or question 6, and so on. It could only be integral values. So in this case, we use a discrete graph because test numbers can only be whole numbers or integer or like natural numbers. Okay. I think that kind of explains it a little bit more.
Yeah, hopefully that made sense for you guys.
Yeah. Should we move on to functions?
I think we should.
Okay.
Okay. So so we're going to talk about functions now. So a function is essentially the same as a relation, especially not especially, but a function is like a relation, but but there can only be one value per one dependent variable for one independent variable. I'm not sure if that explained it well.
I guess where 1x can only have 1y.
Yeah, that's a better way to do it. Yeah. So you can't have something like x is equal to 1, but y could also be equal to 1 or 2.
Yeah.
Yeah, so we can actually kind of do this with the mapping thing again.
Mhm.
Yeah. So a function would mean that from each independent variable, there's only one arrow. Wait, okay. For each dependent variable, there's only one arrow pointed at it. So for this to be a function, it will mean that the number of arrows has to be equal to the number of independent variables.
Wait, but I'm pretty sure like
Okay, wait, I'm confused now.
yeah, because okay, I think what you meant is like for each independent variable, there can only be one arrows that comes out of it. So for example, if we look at the number 1, we could only have one arrow that comes out of it. If the number 1 has 2 or more arrows, that will mean when x is equal to 1, y can either be 1 or 3, and that would not qualify for a function because in a function, 1x only has one y value. Because David, what you said, like because like what I think what you meant is 3 cannot go to 1, but I think like in a function, 2 x values can map to 1 y because that would just look like
Yes.
this, right?
Yeah.
Okay, anyways, so a function, to summarize it up, a function is where 1x can only go to 1y, can only have 1y. Do you want to explain it, like what it will look like on graph?
Yeah. Okay. So we can do a little bit of identifying right now. Okay. So we can have a function. So for example, up until this point, we were working with a linear equation. So for example, a linear equation would be a function because if we just draw a linear equation, for example, y equals x, this would be a function because for every x value, if you look at it, there's only one possible y value. So for example, if we look at something like x is equal to 1, the position at 1, its y value will only be like 1 if it's y equals x. There can't be like there can't be two y values for it. So if we like do x is equal to at the okay, if we draw okay, we're gonna talk about vertical line test. I feel like that's gonna make a lot more sense.
Yeah, or we can just be like, if the function looks like this, then this would not be a function because 1 can correspond to 1, or it could correspond to like another number like 7.
Yes.
Yeah, okay.
So
I think now is a good time to talk about vertical line test.
yeah, so the vertical line test is how we test if something is a function. So in this case, to perform a vertical line test, what we would do is that we literally just draw a vertical line. So at any point in the graph, we just draw a vertical line.
An
And
imaginary line, of course.
yeah. And if that line only passes through one value, then that would mean this equation would be, well, not really equation, this graph will be a function.
Yeah.
So, and it should be like any point on the graph. Just pick some spot at random, draw a line, and if it only crosses over one point, then that will mean the graph is a function.
Yeah.
So we can draw something that is not a function, like a sideways parabola.
Sure.
Yeah. So if we perform the vertical line test here, we draw just a vertical line. We see that it actually passes through two different points. So one at the top where it's going up and one at the bottom where it's kind of going down. So this would not be a function.
Yeah. In a function, every single x value has to have only one point. So in a vertical line test, like what David said, just move it from left to right. Basically, like you want to scan the whole graph with a vertical line.
Yeah.
Do you want to do like another example that's not a function?
Sure. We can draw like can draw a love heart.
Love heart.
Just draw a heart. I mean, I don't think it would be a function. Yeah, for example, if we draw like at a random point, we just do a vertical line test where you just draw a vertical line. We can see that it passes through two different points. So this would not be a function.
Yeah.
Yeah. And if just at any point there's 2 points, if you're doing if the vertical line test fails, then the entire graph is not a function. So maybe you could have like one value where it's just you can't do the vertical line test on, then that entire graph would just be not a function.
Yeah. Exactly. So every single value has to only have one. I guess we could do some like practice questions for them to like decide if it's a function or not.
Yeah, that's a good idea.
Okay. So for this graph, so for this graph, classify as either a function or not a function. It's a function. Yeah.
Yeah, you know, the first step makes it very questionable.
Okay, that's a drawing error.
It's
Does
fine.
that make
It's
it a
fine.
little bit clearer?
Yeah, I think that does. Yeah, it almost looked like a vertical line for a second.
Oh, okay, yeah.
Yes.
Yeah, it's a function. Good job. Because if we apply the vertical line test, every single x value only corresponds to one y value. Like this is true for every single x value. What about this graph? Is that a function or not a function? Not a function. Yeah. David, do you want to explain it?
Yep. Okay. So if we start doing the vertical line test from left to right, we notice that it starts off okay. The vertical line test works perfectly fine until we get to this part where it kind of folds over on itself, where we actually can pass through 3 different values. So this will mean that the entire graph is not a function.
Yeah. Okay. What is next? Do you guys feel confident with like functions? Yes? Okay, awesome. I think that's all for this lesson. So
Yeah.
should we do some worksheet problems?
Yeah, wait, there's this interesting problem on the thing. Not on the worksheet. Not on the worksheet. Okay, here, put this in chat. Okay, so out of all the possible slopes, which slope give a line that's not a function?
Oh yeah.
Yeah.
Okay.
Actually, is that even possible?
Yeah, it is.
Oh yeah, it is. Okay. Should we just tell the answer?
Sure, you can do it.
Okay. So when we have a slope, we kind of assume it's a vertical, like just a straight line. So of all the possible arrangement for a straight line where it can fail the vertical line test, it's when it's directly just basically vertical. So a vertical line would obviously fail the vertical line test because it passes through all the possible values. And a slope of a vertical line, which we talked about earlier on in a previous lesson, is undefined. So an undefined slope is not a function.
Yeah. Or I mean we could say infinity or negative infinity, but
Yeah.
like yeah, it crosses at every single point on this line. So slope is undefined.
Yeah. This line failed the vertical test really badly.
Yes. Yeah, this lesson ended pretty early. But we can still do some worksheets problems, Edward. So do you have any like problems that you want to do?
Not really, but also this worksheet is laid out a little weird. So after some point, you start getting into lesson 11.
Oh, really?
Yeah, so I think past question 8,
Oh,
that's like not in lesson 10 anymore.
oh, okay, I see, I see. Uh, I don't think 8 is in our lesson as well. So,
Yeah. Huh.
oh, we
Yeah,
can
we
do
can.
number 3.
Yeah, question 3 is pretty easy. Yeah, if you guys have the answers, you could just put it in chat.
Oh no, forgot. Okay.
Oh, remember now.
What's that? Oh, okay. Yeah. Yeah, exactly. It can be changeable.
Yeah, so one value, the dependent value relies on the independent value.
Yeah, exactly. You didn't forget. Good job. Also, classify if it's discrete or continuous graph.
Oh yeah, it's a pretty good one.
Yeah, because there aren't any like discrete continuous questions.
Yes, that's correct.
Yep. Also, do you think it's discrete or continuous? Discrete. David, what do you think? I'm pretty sure it's continuous, actually.
Yeah, I think it's continuous as well. I think they could have made it clear if they put something like studying hours or something.
Yeah, exactly. So I mean, it's
Yeah,
really hard
that's
to
true. Yeah, maybe you have a teacher that's still using like the 1, 2, 3, 4 method.
Yeah. Well, in this case, you mentioned correctly that studying is independent. So we're looking at if the number of hours studied can take on any value, right? So I mean, I could study for an hour. I could study for 2 hours, but I could also study for something like 0.5 hours, or I could also study something like pi hours. So I
Whoa.
mean, unless you're doing the Pomodoro timer or like you're in school being forced to study, you can study for how many number of hours you want. Like it could take on any single value, right? So since it can take on every single value, it's continuous.
And yes, that's also correct for number A.
Yeah.
So I think an easier way to think of like which one's independent and dependent is if you like try to like kind of put it into a sentence, right? It's kind of like, oh, A is continuous. Yes, it's continuous.
So yeah, David, what were you saying about sentence?
Kind of like if you were to like think it out a little bit, like the distance depends on the speed. Okay, wait, yeah, I don't know if that makes it better.
Yeah, it does. Distance depends on speed. Test grades depends on studying. So
I mean, I wouldn't blame you. The question's worded kind of weird.
yeah, if it's like amount of time spent on studying, it would be much easier.
Should we do question 4 as well? Because it's like right underneath it and it's pretty easy.
Oh yeah, sure. Function. Determine if the table of values is a function or a relation. Relation.
It's a
Can you please
function.
explain why it's a relation?
Yeah, I think.
Well, explain why it's not a function. Oh, okay. That kind of makes sense. So, Edward, essentially what you're saying is that a function is any equation that has a formula. But the definition of a function is actually one x value can only correspond to one y value. So in this case, 9 corresponds to 55, 10 to 56, and 11 to 60. So any x value is only corresponding to at most one y value. I mean, Edward, yeah, I kind of get what you're saying. Um, Usually that's the case, like every single function will have a formula, but in this case, it's all random. Like there is no formula, but it's still a function.
A relation would be just any like way to relate one value to the other.
Yeah,
So a function is a relation, but a relation is not necessarily a function.
yeah, exactly.
Doesn't have to be a formula. Neither does a function have to be a formula. it can just be like if you have a, for example, a table of values where you just put a bunch of random numbers, and if for every x there's only one y, that table would still be called a function.
Yeah. And for Edward, actually you're very right about like every function being a formula, but like I think you'll learn that in grade 11. So for this case, the function looks something like this. Like there is one line that looks like, whoops. Huh, interesting. One line that looks like this, and then another line that quickly jumps up. So you said how there is no formula for this, but there is actually a formula for this, and it's called a piecewise function. What that means is that there's a formula for every straight line. There's a formula for this part. There's a formula for this part. But anyways, I won't get into too much detail about that. Just remember, like, a function is when one x only goes to one y and not two y's.
But what about a relation? A relation can have a formula technically.
Yeah.
Yeah, like a formula for a circle that would not be a function, but it would be a relation.
Yeah.
You know, like x squared plus y squared is equal to 25. That would be a formula of a circle.
Well, it doesn't have to be a formula, but could you explain why this isn't a relation? It is a relation. Basically,
Yeah.
everything you see is a relation.
Honestly, yeah, this question could have probably been worded better as well.
Yeah, everything you
Yeah.
see is a relation.
But try to be as specific as possible.
Yeah. Okay, I guess if this makes sense, we can draw a Venn diagram. So this is all the relations. This is the functions. If that kind of makes sense. Like functions are a part of relations. Uh, David, do you have a question? Wait.
Yeah. Yes. But does that mean?
Yeah.
Yes, you will be correct.
Yeah.
Yep. Yeah, we could have like for a relation, we could have something like, for example, a bunch of ordered pairs where it's like 1, 1, 2, 1, 3, 1, 4, 1, 5. Yeah. If you were to like graph this out, this would be a relation.
Or better yet, we can say like not a function
Yeah, that's true.
because everything is a relation. Not a function. Could you give an example? Sure. So wait, David, is that like, were you answering his question? Like,
Yes, but I think we could give a better example. I think we could do like the age thing again. For like the table above, the age thing. Maybe we could also have a 12-year-old who's also 55 inches.
oh, okay, sure.
Yeah. So right now, this table is a function. However, if we have like did another survey and we found out that there's a 12 years old, a kid who's 12 years old, and he's also 55 inches, then this table would not be a function anymore.
Wait, David, I'm pretty sure it's still a function.
Wait, what?
It's still a function.
Oh yeah, wait, I'm dumb. Okay. We could have another 9-year-old. We could have a 9-year-old who's like 70 inches.
Yes.
Yes. Now that wouldn't be a function.
Yeah, because one x is going to two different y's. That's a tall child.
Very true.
In this case, it's like a child is like this, but he's in a superposition of being short and being tall. So that wouldn't really be a function because it doesn't really make much sense, right? Graph each function. I'm pretty sure we did that last lesson.
Yeah. write
Uh,
the equation.
of a relation. That's not a function.
I mean, that's pretty easy.
Is it though?
Yeah.
What's your equation?
X is equal to 3.
Oh yeah, that's true. Okay. I was thinking of a circle.
Oh, okay.
Yeah.
Yeah, that's a more big brain solution.
Nah, x equals 3 is a big brain solution. Wait, what?
Oh, just a line through everything.
Yeah. Wait, okay, what is going on?
Oh, it's bad. Okay,
Oh,
we
just
should do
start.
number 7.
So if we have an x equals 3, it obviously fails the vertical line tests because it does. On number 7,
Yes.
what is the solution to
Wait,
f?
f of x is... I don't think we talked about that yet.
Well, it's pretty self-explanatory. Like,
That is true.
so basically think of this as for what x is y equal to 2.
So for the y is equal to 2 thing, just find the points which have a y equal to 2.
Yes.
And you don't have to put the x value. You can just put like the letters for the point.
Yeah. B and D, yeah.
Yes. And is it continuous or discrete or discontinuous? I don't know why they phrased it like that.
This discontinuous and discrete are the same thing.
Yes, it looks discrete and is discrete.
Yes.
And is it a function?
No. Why not?
Because there's two, yes.
Yeah, exactly. So when x is 2, it could either be 3 or it could be -2. So yeah, you're absolutely right. Good job. Do you like have another question in mind?
Not really. I think we pretty much covered everything.
Yeah, I
Every
think so.
possible question.
Yeah. Same with x is -2 and 4. How so? There's only one y value for -2.
You just do that again?
Yeah, sure. So I don't think you're here for the early part, but for a function, it's basically when one x value only goes to one y value. So in this case, it would not be a function because when x is 0, it goes to two y values. It goes to this value and this value.
Oh, yeah, I missed most of the reading, so yeah.
Oh yeah, that's fine. We'll post this video on our YouTube channel. So
No, well, yeah. Thanks.
okay,
Bye.
see ya.
See you later.
Yeah, Edward, about that. So although there's 2 points which have the same y, we gotta also think about the x. So for example, when we have x is equal to 4, it is only equal to 2.
Okay, Edward. So
Yeah.
what you're saying is that like one y value goes to two x values, but if we want to classify a function, okay, yeah, I know a lot of like people think this. This does not have to be true for a function, but this does have to be true. Yeah, it's x then y.
Yeah, and remember the vertical line test as well.
What is going on? Okay.
Oh.
Okay, so this is a function, even though like it fails the horizontal line test, which isn't a thing. But this is not a function because it fails the vertical line test.
Edward, I think you got that mixed up a little bit. It's 1x and 2y is equal to non-function.
Yeah.
I guess another way to think of this is if you to put it into a table of values and you see the same x appear 2 or more times, then it wouldn't be a function.
Oh yeah. That's a good way to think about it.
And-
1x to 2y is a non-function. Yeah, exactly.
Yes.
2 or more y's, I guess.
Yeah, and the y has to be different values, obviously.
Yeah. Yeah.
Yes.
So x equals 3 would look like this. Correct me if I'm wrong.
Yeah, that will look like that.
Yeah. This one? Or like, you can tell me when to stop. Oh wait, okay, this one. Alright, got it? Alright, nice. Okay, does anyone have more questions? Alright, we'll take silence as a no. Oh wait, one more.
Yeah.
Yeah, exactly.
Yeah, so for the x3, it's technically every possible y value. So
Yeah. Yep,
So
no
it is-
problem. Hope you learned lots.
okay, thank you guys.
Yeah, thank you guys. See you next lesson.